We are taking you on a journey to Switzerland, in the heart of Europe. In the northwest of Switzerland is the canton of Jura, where beneath the Jura Mountains, the underground research laboratory of MtTerri is located. The geology of this region is complex and features a thick layer of opalino clay from the early Jurassic period 175 million years ago. When considering the deep geological storage of radioactive waste, this formation is of particular interest to researchers because opalino clay is almost completely water impermeable and is therefore considered an alternative to the disposal in crystalline or salt rock. The laboratory can be accessed via the MtTerri motorway tunnel, starting near the small city of Saint-Ouzan. The laboratory is used for research purposes only, and no radioactive waste is or will be actually stored here. Instead, a large number of experiments are conducted regarding the development of methodologies and the characterization of opalino clay. The MtTerri project began more than 20 years ago, and the tunnel system has been extended multiple times since. The large southern gallery has just been excavated within the past 2 years. Demonstration experiments allow tests on a 1-to-1 scale to be carried out over a long period of time. Many experiments are supported by numerical simulations for planning purposes and process understanding. Within the next few minutes, we would like to show you a few of these experiments. We are starting with the full-scale emplacement experiment. Simulation of this involved not only the experiment itself, but also the excavation process of the small tunnel and the mechanical stress involved. After lining the walls with shotcrete, 3 heater elements have been placed in the tunnel to simulate the effects of the heat emitted by radioactive waste. The tunnel has subsequently been filled with various insulating materials, and sensors are measuring a variety of parameters in the now sealed-off tunnel. Numerical simulation shows the effects of a slow increase of the temperature emitted by the heater elements, including the heat propagation within the host rock, the subsequently decreasing saturation of the clay, and the mechanical stress and strain caused by these thermal changes. Model results are used to evaluate the safety of the storage of radioactive materials within this rock formation. A second experiment investigates the effect of seasonal cycles this deep below the surface. 2 niches have been excavated and are heavily instrumented. One is sealed off to avoid desaturation. The other remains open and is exposed to seasonal and annual changes based on the climate within the tunnel system, visible here in the form of expanding and retracting surfaces in extreme time-lapse. Deformation, desaturation, pressure, and many more physical variables are both numerically simulated and observed over many decades. Only a few meters away, the DRC experiment is currently being planned, supported by first numerical results. Again, 2 boreholes have been drilled. Both heated water and chemical tracers will be inserted in one, and multiple parameters are measured in the other, to observe the effects within a short distance. Roughly 140 experiments have been conducted in the MtTerri Rock Laboratory within the past 20 years. Some are finished by now, some are still running, and new ones are still being started. The aim of these experiments is to improve our understanding of the processes involved and to design safe underground repositories. Scientists from many research labs and federal or state offices all over the world are working on these experiments. We will finish our little tour with a look at the fault slip experiment. Here, fluid is periodically pressed into a fault zone, located within the layer of opalino clay, to observe the effects of increasing pressure. Reactivating the fault in this way results in deformation and a minuscule slipping of one layer of the other, which in turn permanently widens the fault and increases possible transport processes within. Besides all the experiments conducted below MtTerri, many new measurement and evaluation methods have been developed within the course of this project. It has advanced the determination of rock parameters using innovative borehole geophysics and gained a new understanding of the fusion and retention processes of radionuclides in and through claystones. All of these methods are also applicable to low permeability rocks at other sites. Many thanks to Swiss Topo, the BGR, and the OpenGeoSys community for providing the datasets and models used in this presentation.